We are doing an in-depth look at problem number 13 from section 3.6. So it says, suppose the position of an object moving horizontally after t seconds is given by the following function. So the first key is moving horizontally. So that's why I have the horizontal line here. And the time is in seconds. So I'm going to note that here. Time, which is t seconds. Let me back up. Seconds. And we have to realize that this is the position function. You should know the derivative of the position is velocity, and the derivative of velocity is acceleration. We'll talk more about that. And s is measured in feet, so the units of the position is feet. And s greater than 0 corresponds to positions on the right. So we need to note that. We have a center point 0. S is positive here, and S is negative on this side. So to the east is positive, to the west is negative. So we're setting up how things basically look. If I'm moving right, I'm moving in a positive direction. Left, I'm moving in a negative direction. All right, the first step, graph the position function. So what I'm going to do, you could do it in your graphing calculator or Desmos. You should be able to do it in either one. So we're going to go to Desmos and graph that. 2t cubed minus 21t plus 60. 2 minus 21 plus... Oh, what a quinky dink. I already have it set there. Now, you have to be careful because your windows might be off. Suppose your graph looked like that. Well, first of all, you want to go from 0 to 6. So you want to squeeze down and get it all the way to 6 seconds, which is here. Now, your graph could, and this is important, I'm going to change this. What if your graph looked like that and you have your 6 seconds and you want more of the graph above? So what you should notice, the top is at 40 right now. If I go to my settings, I want to make the top one bigger than 40. What happens if it's 50? That's not big enough, I can see. Let's make it 60. All right, that works. Now I have the whole graph in the frame, and that's what it looks like. So let's go back, and I have the graph here. So that is a graph of the position function. Now let's make some connections here. And you need to kind of process through this and make sure you understand what's happening. So after 1 second, he is 40 feet away. That means to the right. So he's going to move this way, and after 1 second later, he's going to be 40 feet to the right. Now, if you go for another second, at this point here, now he's going to be what, 50? So I'll label these in arrays. So suppose this was 40, that's 1 second later. And then he's going to be at 50, and that's going to be at 2 seconds. So you can see the person or this particle's moving to the right up to 2 seconds. Now, after 3 seconds, what is that? I don't know, about 45? So I'm going to use a different color. It starts going backwards. It's going to be at 45 at 3 seconds. And then let's look at 4 seconds. At 4 seconds, I don't know, that's about 30 something, a little bit bigger than 30. So I'm going to make up a number. I don't know. That looks like about 32. And that's after 4 seconds. And then let's look at 5 seconds. Right there. Looks like that's 30, 25-ish. So I'm going to put a 25, and that's going to be 5 seconds. So the corresponding what's happening, and you need to see this. So it's moving to the right, and it's going to stop after 2 seconds. As you can see, it's going to start moving back towards the starting point. So it's going to turn around and start heading backwards. So after the 5 seconds, it's back there. Then look at 6 seconds. At 6 seconds, what is that? This is 30, 37 away. So it's turned around, it's going back the other way. And so you need to be able to see, I'm moving away from the origin, back towards, and away. I'm moving away, back towards, and away. So you need to kind of get a feel how all this stuff fits together and works, and how the graph connects to what the object is doing. So that's part A, graph the position function. Part B, find and graph the velocity function. So this is an important step. You have to understand velocity. The velocity is how fast your position changes. That should make sense. If something moves a large distance over a short amount of time, you would say, man, the velocity is high. So it's measured by change in position, which is s, over change in time. But our function's f, you could also say df dt, because our position function's f, but it's also defined as s, so you can look at it either way. So the change in f over change in time, you should understand that is the velocity, and in this case it's going to be f prime of t, because that's the equivalent to that. So we take the derivative of this using the power rule. So the 3 comes in front, that becomes a 2. As we continue through that, we get 6t squared minus 21t plus 60. We have a velocity function. Now we would graph that. Again, I can do it in Desmos. 6 minus 21, 60. Hey, uh-oh, did I make a mistake? I think I did. Good thing wow. Did I write the function down wrong? Let me check this real quick. If I did, I'm a very sad man, because I'm wasting time in this precious video, and I'm wasting your time. Oh, that's a squared. I know exactly what happened. Let me go back and fix this. There's a squared right there. And so it's going to be 42 on this. There we go. That makes more sense. So I have it here, and there's a graph. It's a parabola. So that's the graph I have pictured there. So I found the velocity, I graphed it, and then we have a question based on this graph. And we'll do it 2 ways actually. When is the object stationary, moving to the right, moving to the left? Well, it's stationary when the velocity is 0. So we're going to set this velocity equal to 0, factor out the 6, and we're going to get that. This factors to t minus 5, t minus 2, so we get t equals 2 and 5. Those are the times where the velocity is 0. So that matches with our graph. If you look at our graph, right here at 2 and right here at 5, we have the velocity is 0. So that totally matches what we have on our graph. Now, here is what we have to look at. We're going to look at the graph in this region here from 0 to 2 seconds. Now, this is where you have to understand this is the graph of the velocity. This is v of t. Because of that, v of t in this region is positive. It's positive. Why? Because it's above the x-axis. If I asked you, is this graph positive or negative, you wouldn't hesitate and say, oh, it's above the x-axis, it's positive. But sometimes you think, oh, velocity, it's a slope, and you say, oh, it's going downwards, it's decreasing, the slope's negative, the velocity, but that would be, if this was a position function, you could look at the slopes to get the tangent lines, but this is the velocity. So it's negative there. In this region between 2 and 5, we can see the velocity is negative because it's below the x-axis. And then from 5 to 6, we can see that the velocity is positive. Now, if the velocity is positive, it's moving to the right. So it's moving to the right. Between, you can see 0 and 2, so from 0 to 2, and from 5 to 6. Now, this can be an interval or it can be a point. 0, 2 could be a point, and 5, 6 could be a point, or it can be the numbers between 0 and 2 and the numbers between 5 and 6. But since we're describing where it's moving right, and they wanted the regions, these are intervals by context. Now, where is it moving to the left? So something moves to the left when the velocity is negative. And that we can see is between 2 and 5. So we can say in that region from 2 to 5. Now, how does that work logically? Let's go back to this number line here. So velocity is change in position over change in time. Now, if that comes out to be positive, if that's greater than 0 or positive, that means your change in position is positive because time is progressing forward. So that's always going to be positive. Well, what's your change in s? That's your final position minus your initial position. So in order for that to be positive, that means your final position must be greater than your initial position, right? That's got to be bigger than that to come out positive. For your change in position to be positive, your final must be bigger than your initial. Well, if you start here, where is it the distance bigger? To the right. Bigger numbers are to the right. So that tells you if your velocity is positive, you're moving right. Even if you're in a negative value, if you want a bigger value, you have to go to the right. So if your velocity is positive, that means your position is getting bigger because your final has to be bigger than your initial to get a positive. So you have to be moving in the direction of bigger numbers, which is to the right in this case. So that's why positive velocities is right, negative velocities is to the left. And that takes care of part B. Part C, determine the velocity and acceleration of the object at t equals 1. Well, we already have the velocity function. We just found that. So v of t is 6t squared minus 42t plus 60. So if we want that at 1 second, we just plug in 1 and we get our answer pretty quickly. So that's going to be 66 minus 42. 40, 50, 60, 20. I'm getting 24. And the units. Okay, let's talk about the units for velocity. ds, dt. S is position, and we know the units is feet. Our feet, the units are feet. And time is seconds. So we get feet per second. So this velocity technically should be feet per second. And that's the units of that. So that's v1. All right, so let's look at acceleration. How do we get acceleration? You should know the acceleration is a derivative of the velocity. And why? Let me just do some side thoughts here. Acceleration is really how fast your velocity changes. Now think logically. If something is accelerating quickly, its velocity is changing quickly. So acceleration is how fast the velocity changes compared to time. Well, dv dt is v prime of t. So that's how we get that. The derivative of this function over here, we can quickly get 12t minus 42. And the question asks, what's the acceleration at 1 second? So that's going to be 12 times 1 minus 42. And we're going to get negative 30. Now, what are the units for that? Let's look at this. The units of velocity is feet per second. The units of time is second. So technically, you could say the units are feet per second, which is acceptable. But how do you divide two fractions? You multiply by the reciprocal. So if you flip seconds, you get 1 over seconds. And so you end up with feet per second squared. So another acceptable form is feet per second squared. So those are the units, and that's acceleration. All right, let's continue on. Part D. Determine the acceleration of an object when its velocity is 0. Okay, that means the velocity is 0. Yeah, that's quite profound, isn't it? So we take our velocity function and we set it equal to 0. Now, I could factor the 6 out. That's not right. That's 7. Oh, I actually did this earlier, didn't I? I did. So it's going to be minus 5, t minus 2. And so 2 and 5, those are the two times where the velocity is 0. They want the acceleration at that time. So I do a of 2 and a of 5. I plug that into my acceleration function, which I have above. That's 24 minus 42. And I have to do math. 6, 8, 18. And we know the units are feet per second squared. These should be seconds. I plug in 5. That's 12 times 5 minus 42, which is 60 minus 42. And I believe that's also 18 feet per second. Now, oh, the first one's negative. I thought they were different. Okay, that's part D. Part E, on what intervals is speed increasing? You have to know speed is dependent. The speed increasing is dependent upon the velocity and the acceleration. So if I go back to Desmos, and now I graph the acceleration, those are the two graphs, acceleration and velocity. And so I'll go back here and I have it already drawn. Where the green is acceleration and the purplish, let's see if I can have that color. It looks like this is velocity. Now, it all depends on whether the velocity and acceleration are positive or negative. So we're going to look at regions. And here's the first one, from 0 to 2. Why from 0 to 2? Because you'll notice at 2, the velocity changes signs right there. So I want to look at the region between 0 and 2 before it changes signs. And my question is velocity positive or negative there? And the next question, is the acceleration positive or negative there? Now, I claim the velocity is positive and the acceleration is negative from 0 to 2. And why? Again, what determines if a function is positive or negative? If it's above the x-axis, it's positive. If it's below the x-axis, it's negative. Look, velocity above the x-axis, positive. Look, acceleration below the x-axis, negative. And therefore, in that region, speed would be decreasing because, what's the reason? Velocity and acceleration have opposite signs. I'm not going to write that down, but that's the rule. If velocity and acceleration have opposite signs, speed would be decreasing. All right, that's region 1. Now, if you look at 3.5, it crosses. The acceleration changes from negative to positive. That's going to be region 2. What do you know about velocity in that region? And what do you know about acceleration in that region? I claim that velocity is negative and acceleration is negative. My reasoning, they're both below the x-axis. They're both negative. And what you have to know when velocity and acceleration have the same sign, speed is increasing. So I would say speed is increasing on that region. My next region, we see that the velocity crosses at 5. So region 3 would be from 3.5 to 5. We're going to look at velocity. We can see velocity is positive, and we're going to look at acceleration. I got that backwards. Velocity is negative because the purple line is underneath the graph, and acceleration is positive because the green line is above the graph, above the x-axis, excuse me. And therefore, since the signs are opposite, in this region, we can say speed is decreasing. And my last region is up to 6, because that's the domain that they gave us. And hopefully you can quickly see that the velocity is positive, that acceleration is positive. Therefore, since the signs are the same in this region, we can say speed is increasing on that region. Hopefully this was helpful, and that's it for this lesson. Bye.